Hi everybody, I'm Mr. Marshall, your physics teacher. I'm going to start out with a little review. We'll talk potential energy and work, then we'll talk kinetic energy, which has a new equation, and then we'll talk about the ways that you do work to give an object energy. When it has energy, you can use that energy to do work. So it's a circular type of thing, but that's our work and energy principle. So work. Work is basically when you're applying a force to move something a distance. You have to accomplish something when you're talking about work. The example, the woman's pulling a crate. The work that she's accomplishing is how much force she's pulling in the direction the crate's moving. So even though she's pulling up and at an angle, we need to use that cosine theta, cosine of the angle, to figure out how much of the force is acting parallel to the displacement. That's the force that's doing work. The force that's pulling up is not doing any work because the crate is not moving in the up direction. That's important. Work has to accomplish something.
Gravitational potential energy is when you do work to lift an object up. And in this special case, the force that it takes to lift an object is equal to the weight of that object. And you get the weight by taking the mass and multiplying it by the acceleration of gravity, which is 9.8. So the calculations for work done to lift an object are the same. The work is equal to the potential energy, so it should be logical that those equations would be the same thing. Instead of force times distance that works in any direction, we're specifically looking at the weight, mass times gravity, times the height. And for height, we just use the y coordinate. Kinetic energy is where we left off on last week, I think. Potential energy involves position, where kinetic energy involves your velocity. Like kinetic friction was friction of a moving object, kinetic energy is the energy specifically related to motion. The faster you're moving, the more kinetic energy you have, whereas the higher up you are, the more potential energy you have. So our equation is new, and it's half of the mass, and that's a calculus thing, times the velocity squared. So velocity has a huge effect on the energy of a moving object. Now, the work energy principle means that you do work on an object. Whenever you do work, whenever you apply a force over distance, you're going to change the object's energy. That could be increasing the potential energy, such as lifting it up, or it could be increasing the kinetic energy. And rather, I should say, changing the kinetic energy. Here's an example of a bus. Boom, circle. It has a velocity. If you apply a force, this could be the gas pedal. If you apply the gas pedal, your velocity will increase. That means you've done work to it. The engine has applied a force over some distance. You've done work, and that work has increased the speed of the bus. We could also interpret this to say that the force is going in the opposite direction. If you have a velocity and you hit the brakes, the brakes will apply a force in the opposite direction, slowing the bus down. That would be negative work, and you're removing energy from the bus, decreasing the amount of kinetic energy it has. The amount of work the brakes do is equal to how much kinetic energy you've removed from the bus or how much you've slowed it down. That energy is lost in heat, lost to the environment. You make hot brake pads cool down, that energy is lost. It's non-conservative, and that's something we'll be going into a little bit later.
Here's a list of the different types of energy. You should take a minute to read them. I think the slide is fine, or pause, whatever. Gravitational potential energy we talked about already. Elastic potential energy is, it's what it sounds like, a rubber band or a spring. And when you take something like a Nerf gun and you pull the spring back, it then stores that energy. You did work on a Nerf gun. You compressed the spring, applying a force over a distance. The work that you did is stored in elastic potential energy. When you release it, you give kinetic energy to the dart. Chemical potential energy is like a battery, or a hot pack, like a keep your fingers and toes warm type of hot pack. Kinetic energy we talked about, energy of motion. Thermal energy is what happens when energy is lost, basically. When you apply the brakes in your car, you have kinetic energy, your brakes do work, your car stops. Where does the energy go? In this case, it's lost to your surroundings in thermal energy, meaning you heat up the brakes and that heat is useless. Now, hybrid cars can actually take some of that kinetic energy and use it to recharge your batteries. So it doesn't have to be lost. And we're learning more ways to not lose as much thermal energy. But when we talk about mechanical energy, it's the sum of all of your potential energy and your kinetic energy. Thermal energy we can't recover. So thermal energy is not mechanical. But we can trade potential and kinetic back and forth, and that's what we do on a roller coaster. So this is a sad slide for me because it's a demonstration that I do in class where I take two large metal ball bearings and I smash them together, and that's enough heat to burn a piece of paper. It's a cool demo, but essentially what happens when you take two 1 kilogram ball bearings and slam them together at 20 meters per second, the energy is released in the form of heat. We can calculate how much energy it has because we have a mass, we have a velocity. I said kinetic energy here. In the future, you're just going to see how much energy does it have, and you have to think to yourself, well, are they up high? Is it potential energy? Is it a battery? Is it chemical? It's never going to be a battery. No, this is kinetic energy because it's moving. So we're going to do 1/2 mass velocity squared. 1/2 times 1 times 20 squared. And that will tell me how much energy is released with one ball bearing. I did go ahead and make it 2 ball bearings because that, again, ties into the demonstration that I would ordinarily do in class. If you want to see what's up with that demonstration, this is a picture of something really similar to that demonstration. So go ahead and check that out. Once you do that 1/2 times the mass times 20 squared, you'll get the kinetic energy of 1 ball bearing. And you should see that work out to be something like 20 squared is 400. 1/2 of 1 is 0.5. So each ball bearing will have 200 joules of energy. Each one does. 2 of them will have 400. So I'm going to ask you a question like this at the end using forms like I did before.
Here's an example using a larger mass, a realistic mass, the mass of a car. So this is looking at how much kinetic energy a car gains when it increases the speed. We will later talk about how that energy, if you crash, turns directly into heat, which is why action movies tend to show cars blowing up, because they do have a lot of heat generated when they go from a high velocity to a 0 velocity. The problem is telling you kinetic energy, so you should immediately think, well, how does it fit into a kinetic energy equation like this? And what's happening is this car, and I know right away I have a mass, so that's a good start. A 2,000 kilogram car is going to gain some kinetic energy when it accelerates from an initial velocity to a final velocity. Now, I have to take a second and make sure we're clear on a little bit of math facts. We're looking for the energy when you change the velocity, and we have a change of 30 meters per second is a delta V. So we do care about that change in velocity, but this is the question that I want you to be clear of. Can you just use the change in velocity of 30 meters per second in for this equation? And the answer for that is a solid no. And it has to do with math, order of operations stuff. And I just popped this here as a quick example that you can run through as to why that does not work. I'll let you do that instead of confusing you with lots of numbers. What we need to do is to plug in the velocity squared for each one of these. We can simplify it a little bit because we are doing it's accelerating from, we're looking for the change in energy, mass velocity squared. So change in velocity from the final to the initial. So we can simplify it a small amount because they both have the 1/2 mass term, but we have to square each term individually, and you'll be doing this in the forms assessment at the end of this. So this is our kinetic energy for this problem for you to look at later.
So we're going to end here simply saying work is your change in kinetic energy. If you're doing positive work, you're increasing the kinetic energy of the system. So if I give a skateboard 10 joules of energy, its kinetic energy just went up by 10 joules. However, if the brakes do 1,000 joules of energy on a car, the brakes just took away 1,000 joules of kinetic energy from that car. So that's kind of how it works, and I think that's where we should end here, and I'll give you a couple forms questions based on the kinetic energy principle that we just did.